Hello, I'm Dr. Jacob Hudis. Today we're diving into the fascinating world of flux. We're going to be solving problems. I'll guide you through the problems and break down the essential concepts, step by step.
With AI voices to guide the way, we'll learn about flux and physics today.
In this problem, a constant magnetic field of 5 Tesla is directed into the page through a rectangular area of 20 centimeters squared, which is 0.002 meters squared. The inner rectangle is the object that we're finding the flux through. It has an area of 0.002 meters squared. The magnetic field is pointing into the page. These diagrams show the rectangle's orientation as viewed from a rotated perspective. This makes it easier to visualize the angle between the area vector and the magnetic field vector. A. What is the flux through the loop when the rectangle is fully aligned with the field? B. What is the flux when the rectangle is rotated at an angle of 60 degrees relative to the field? And finally, C. What is the flux when the rectangle is perpendicular to the field? Now I'll go on to show you the solution.
In case A, the loop is completely aligned with the magnetic field. Since the angle is 0 degrees, all of the field lines pass straight through the loop. This means the magnetic flux is at its maximum value, 10 milliwebers.
Case B, the loop is tilted at an angle of 60 degrees. Only part of the magnetic field passes through the loop because of the tilt. This reduces the flux to half of the maximum value, which is 5 milliwebers.
Finally, in case C, the loop is perpendicular to the magnetic field. At 90 degrees, no field lines pass through the loop at all. So, the flux is 0 milliwebers.
Now we move on to problem number 2. In this problem, we'll calculate the electric flux through a surface with an area vector given by 2I hat plus 3K hat. The magnitude of the area vector is the square root of 2 squared plus 3 squared, and that's equal to the square root of 13. We're talking about the area of this rectangle. This vector defines the area and orientation of the surface. The question is to determine the flux in 2 scenarios. When the electric field has a magnitude of 4 but is in the x direction, and case B, when the electric field has a magnitude of 4, it's the same magnitude, but now it points in the z direction.
This is a straightforward case. No complicated integrations needed.
To calculate the flux, you take the perpendicular component of the field and multiply it by the area, which is elegantly achieved through the dot product of the field vector and the area vector. For part A, the electric field dot the area vector is this calculation, and it's equal to 8 newtons meters squared per coulomb. For part B, where the electric field points in the z direction, the flux is equal to this electric field dot the area vector, and that's equal to 12 newtons meters squared per coulomb. For this example, there are more field lines piercing the surface in case B compared to case A. The area and the magnitude of the electric field are the same in both cases, but the flux is 12 flux units in one case and 8 flux units in the other.
Magnetic flux has its own special unit called the Weber, while electric flux doesn't have a fancy name and is measured in Newton meters squared per coulomb. Flux always has units of field multiplied by area.
We continue on to problem number 3.
Terrific!
In this problem, we're discussing a vector field that's not constant. It varies. This formula is an electric field. It's a vector field. That means at every point in space, there's a vector. That's what a vector field is. And the vector always has the same x component, but its y component varies as its y position, and it goes as y squared. And its z component also varies as the y position, minus 0.3y squared. The goal of this problem is to calculate the flux through faces A and B of the box in the diagram. This is a Cartesian coordinate system. This is the x-axis, the y-axis, and the z-axis, and I drew a box on top of here. There's a vector field, so there's a vector at every location in space, and this problem wants us to calculate the flux through face A of the box and the flux through face B of the box. Flux is found using the dot product of the field and the area vector. If the field or area change across the surface, an integral is needed. Part A of this problem wants us to calculate the flux through face A of this box. We break the surface into many small patches. For each patch, we multiply its area by the amount of field that pierces through it, and then sum up all the contributions to give the total flux. Each one of these small elements has an area dx times dz, and we calculate the field going through that area, multiply it by the small area, and sum it all up, and that gives us the total flux leaving face A.
In this case, since the field is uniform across the entire face, is it really necessary to do the complicated sum? Can't we just take the dot product directly and save ourselves the extra work?
A good point. In this case, every point on surface A has the same y value, and that y value is 1. And because the electric field is only a function of y, the electric field is constant everywhere along the surface of A. When we substitute y equals 1 into the electric field, it gives us this formula. So this is the electric field at every point on face A. Then we calculate the electric field multiplied by the area vector. The area vector of face A is 2j hat. We take the electric field and we dot it with the area vector of face A. This is equal to 2 newtons meter squared per coulomb. On surface B, the electric field varies. It's not the same at every point. In this case, we need to break the surface up into many small patches. For each patch, we calculate the perpendicular component of the electric field, multiply it by the area of the patch, and sum up all these contributions to find the total flux. This is a formula for the electric field. The area vector for each one of these small patches is dx, the length in the x direction, multiplied by dy. The area vector points in the z or k hat direction. If you take E dot dA, that's equal to negative 0.3 y squared. This component makes it through the dot product. And then you take the integral as x goes from 0 to 2, and as y goes from 0 to 1. This integral is taking the flux at this patch plus 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 the flux at this patch, and it sums them all together. Bingo! And that gives you a total flux of negative 0.2 newtons meters squared per coulomb, and that's the flux through surface B. The flux through surface A was positive. The flux through surface B is negative. Math and physics tutoring with Dr. H. AcePhysics.org. Math and physics tutoring with Dr. Hudis. For the final part of this presentation, I want to discuss how to calculate flux through a closed surface. So imagine we have a point charge and it's enclosed within a spherical surface. We've put a cut here to allow you to see that there's a charge inside there, but in fact the surface is closed. The electric field of a point charge is known to be spherically symmetric. That's a law of physics. We know the electric field on the surface of this sphere is going to point radially outward. We take the sphere, we divide it up into many small area elements, and the area elements will also point radially outward. Then we take the electric field dotted with the area element, and we have to sum that up for all the area elements on the sphere. Now, something to point out is that the area elements vary in size. This is especially evident near the poles where they get smaller. So this area element, which is one of the biggest, is much larger than this area element, which is one of the smallest. So when you're dealing with a spherical surface, the area elements are not the same size. In this example, each one of the area elements was dx times dy, and so they were all the same size, in this case where it's flat. But when you have a sphere, the area elements are not all the same size. If the flux through a closed surface surrounding a charge is given to be 2 newtons meters squared per coulomb, what happens to the flux if the shape or size of the surface changes while still enclosing the same charge? So imagine we have some charge in here, and if you calculate the flux over this closed surface, you get 2 flux units. If the radius of the surface increased but the charge enclosed remains the same, what would happen to the flux? The flux through the surface does not change even if the radius of the surface increases. This is because the electric field strength decreases as the surface gets larger, but the increase in surface area exactly cancels this out. This is the formula for flux in physics, and this is the formula for flux for a closed surface. A closed surface is a surface that has no holes on it. There's no way to get from the inside to the outside without cutting a hole through it. What would happen to the flux if the spherical surface were replaced with a box? The flux is the same regardless of the shape or size of the closed surface that encloses the charge.
For a closed surface, flux is determined by the charge enclosed, much like water flowing from a sprinkler. Imagine the charge as a sprinkler, constantly emitting electric field lines like water droplets. No matter the size or shape of the surface around the sprinkler, the total amount of water leaving the sprinkler is always the same.